Fourier transform representation of periodic signals in particular. So what we have discussed so far is, in the development of Fourier transforms, um, we use that connection with Fourier series to develop Fourier transform for aperiodic signals. Okay, so while our discussion on the development of Fourier transforms representation in connection with Fourier series was focused on aperiodic signals. So you see, the idea was that if you have a periodic signal, then we can go ahead and express this, represent this in terms of Fourier coefficients and complex exponentials which are harmonically related. So a linear combination of such harmonically related complex exponentials can represent a periodic signal. Okay, so what happens if this period becomes infinite? Okay, it becomes very large, so that the signal can be viewed as aperiodic. So if the signal becomes aperiodic, then in one period, the Fourier coefficients that one can evaluate that are going to, because the Fourier coefficients are evaluated, they're integrated over one period, they should be the same whether it is aperiodic or periodic. In this perspective, if the time period is large, for example, what we discussed last time was, okay, we took a rectangular pulse, we said that, okay, this is periodic, and this period is capital T, and then it repeats. Okay, so this pulse was symmetric at 0, and we said that, okay, let's call this xt, right? And then we consider another version, x tilde t, which is periodic version of xt. Okay, so this repeated itself with the same period capital T, right? So so this is just a repetition of what we have discussed in the previous videos. If you've not watched, just go back to your in the playlist of signal systems and just have a look at the parts 30 and 31 of this lecture series. So what we discussed was that, okay, and now this x tilde t is just a periodic extension of xt, right? So so if you see xt is x tilde t if t goes to infinity, right? So if you as a limit when t, the period, goes to infinity, then x tilde t can be viewed as xt, right? There's no difference between aperiodic and a periodic signal. Okay, so within a period, if you evaluate the Fourier coefficients that represents the strength of the harmonics, what are the Fourier coefficients? You see, Fourier coefficients, if for a periodic signal are in one period, this is 1 over t, then integration has to be done within one period. Okay, so let's say from minus t by 2 to plus t by 2, and then you are going to bring x tilde t over here. Okay, and then you have this the exponential e minus j k omega naught t. Okay, omega naught being the fundamental frequency, k being the harmonic. So you see, this integration is the same as, within this limit, instead of x tilde t, we can replace this expression with xt, right? Within this time period, there's no difference between xt and x tilde of t, right? This within the one time period, you have the same pulse, right? So that's one. Okay, so we can replace this. The other thing is that if we apply the limit over here for that t goes to infinity, this basically implies that your omega naught, which is 2 pi by t, becomes small, right? That means that your harmonically related components become close and close together, right? They become very close. The spacing becomes very close. Okay, so this expression, well, this can be written as 1 over t, and I can also argue that, okay, since this xt is only non-zero between a certain time instant, called this minus t1 to plus t1. Okay, so it doesn't matter if I change the limit from minus infinity to plus infinity, and this becomes xt. Okay, and then I can replace, let's say, e of minus jk omega naught k omega naught can be replaced by a continuous variable omega, because k omega naught is such a small quantity. Okay, when t goes to infinity, then omega naught is very small. That means harmonically related components, they become much close to each other. So we can replace k omega naught by, let's say, omega, which can be thought of as a continuum instead of discrete multiple of the fundamental frequencies. Okay, and then dt. Okay, so this part of the Fourier coefficient evaluation in this limit was termed as the Fourier transform. So that means intuitively, in Fourier transform, you have Fourier transform does constitute the Fourier coefficients, which are so much placed close together that they form the continuous envelope as a function of omega. Okay, so AK is the Fourier coefficients, the relationship of Fourier coefficient and the Fourier transform is that it represents the samples, I mean, of the Fourier transform. So if you take the sample of where omega is k omega 0, right? So if you take the sample of any sample in transform domain, okay, at let's say 2 omega naught, 3 omega naught, then that's the Fourier coefficient, right, which is constituting the strength of that particular frequency component and the power that it is contributing in that signal. Okay, so that's the idea. I mean, but this whole picture was limited to the discussion of Fourier transform representation of general aperiodic class of signals. Okay, but this discussion does not mean that Fourier transforms cannot represent periodic signals. In fact, they do. Okay, so we can also develop Fourier transform representations for periodic signals, thus allowing us to consider both periodic and aperiodic signals within a unified context. So in fact, we'll see that we can construct the Fourier transform of periodic signals directly from its Fourier series representation. So the argument is that, okay, if xt is periodic, we are going to, since xt can be expressed in terms of Fourier series, what we can do is we can take the Fourier transform of xt. Okay, so if xt is periodic, now we are going to talk of periodic signals. Okay, so we're going to see how we can express, we can use Fourier transform to represent a periodic signal xt. So that was the case before. So this is the Fourier series representation of a periodic signal that has a certain period, let's say capital T, with fundamental frequency omega naught. So what we can do is we can use this expression xj omega, right? And we can take the forward transform to represent the Fourier transform of a periodic signal, and you will see it turns out that for a periodic signal, the transform is itself periodic, which will consist of periodic impulses in transform domain, and those impulses will have the areas or the strengths which are proportional to the Fourier coefficients AKs. Okay, so you'll see that the resulting transform will consist of a train of impulses in frequency domain with areas of impulses proportional to the Fourier series coefficients. Okay, so this will be very useful representation. I mean, in coming chapters, if you look at the sampling process, then since the sampling process consists of can be modeled by a periodic impulse train. For example, if you have, for example, a continuous time signal, and you want to convert this to a let's say a discrete time sequence, right? So let's say there is a switch which is closing at, let's say, t equal to kt. Okay, k being an integer multiple of the switching time where it closes. So it starts with k equal to 0, 1, 2, 3. So what it outputs is xkt, which is a discrete time sequence, right? So basically, this whole scenario can be modeled from continuous time to discrete time sequence. This whole sequence can be modeled. This whole process can be modeled by a pulse train, right? I mean, it's like multiplying your signal with delta t minus kt, right? So we'll see that this representation of Fourier series is very important in modeling this sampling process. Okay, so basically this is just a multiplication of xt with an impulse train, and then you sum it up to find the sequence xkt, because you see anything multiplied by the impulse function, wherever the impulse exists, the function will have, the argument will change. So from here you can write this as xkt, k capital T into delta t minus kt. Okay, so for example, in the switching process or sampling process, the Fourier representation of periodic signals is very important. Okay, and we'll see in communication purposes, in modulation, etc. You modulate a signal, multiply the signal with a cosine or a sine, and shifts its spectrum to the carrier frequency. Also, there you have the importance of Fourier transforms for representation of periodic signals come into the picture. So, anyways, let's see how we can construct, first of all, how we can interpret the Fourier representation, Fourier transform representation of periodic signal in terms of impulses. So, to suggest the general result, let us consider the signal xt, which has a Fourier transform xj omega, and that's a single impulse of area 2 pi, and that impulse is at omega 0. So this is what the expression is saying. The impulse is having the area of 2 pi. Okay, that's the strength, and this impulse is occurring at omega 0. This is the impulse in transform domain. Okay, this is not an impulse in time domain. This is occurring in the transform domain. So to start with, let's determine the signal xt for which this is the Fourier transform. So what we do is we imply the inverse transform relation to find xt. So this was again, you see the Fourier representation of a periodic signal into aperiodic signal, or periodic signal in terms of exponentials, is again xj omega by 2 pi d omega, right? Because omega is itself a very small quantity. Okay, I mean, since for a very large period omega naught is 2 pi by t, and it basically becomes d omega over here as a limit. When t goes to infinity, then your omega naught, if you recall, was multiplying factor, so it becomes d omega. Okay, if you are going to plug this over here in this expression, you see that there's a cancellation of 2 pi. Okay, first of all, you cancel this out, and then what you're left with is delta omega minus omega naught being multiplied by a signal that is exponential. So what you can do is, since this is a multiplication of a shifted impulse which occurs at omega naught, you can take ej omega omega naught t. Okay, the integration variable is omega naught t out of the integration, because the integration variable is omega, and inside the integration you are left with delta of omega minus omega naught d omega. Okay, so what is this? This is unity, right? I mean, the area of until the impulse is 1, okay, which is in general, so it's minus infinity plus infinity. So the Fourier inverse Fourier transform reduces to ej omega naught t. So what it means is that it has an inverse Fourier transform. This relationship has an inverse Fourier transform of ej omega naught t. And if you notice, what we did is that we proved this one-to-one. Well, the Fourier transform has to be a one-to-one mapping. The transform exists, which is given over here. Then there has to be an inverse signal for which this Fourier transform is valid. And similarly, you can go in the reverse direction to show that this is indeed the case. This is the Fourier transform for ej omega naught t. So what we did was we used the inverse Fourier transform relation. We did not evaluate the Fourier transform of ej omega t in the forward direction. We did this in the reverse direction. Why? Because it's not easy for such signals which do not obey Dirichlet's condition for the convergence of the Fourier transform. For example, in this case, you see, is the signal absolutely integrable? That's the first Dirichlet's condition. Well, that's not the case over here. Is this absolute square integrable? Well, that's even not the case. So, I mean, there is no ut over here or u minus t. So, in fact, the limits will be from minus infinity to plus infinity, right? dt. So that's the first condition. Now, can you see that if this is less than infinity, this integral is converging? Okay, well, that's not the case. Okay, so that is one reason why we have shown I mean, if you recall in the previous, in the last video for the convergence of Fourier transforms, I think it was part 31 of the series, um, we said the Dirichlet's conditions are sufficient conditions to show that the Fourier transform exists. But this does not mean that the Fourier transform does not exist. Okay, this is a sufficient condition to show that the Fourier transform exists, but not necessary. It's not necessary that a signal doesn't obey the Dirichlet's condition, so its Fourier transform doesn't exist. Well, it does exist over here, right? It doesn't obey Dirichlet's condition, but the Fourier transform exists. And how? Well, we have shown this in the reverse manner, that the Fourier transform is indeed, for exponential, the Fourier transform is indeed a delta function. Now, delta function is not an ordinary function. It is defined in terms of its weight. Okay, if you recall, delta omega. Okay, it doesn't matter if it is a function of omega or time, but the definition is the same. It's not defined at omega equal to 0 or t equal to 0. It's defined always in terms of its weight, right? So it's not an ordinary function. That's one thing. The other thing is, you see, this exponential, complex exponential, is not real. Therefore, the Fourier transform is not symmetric, right? The Fourier transform is also single-sided. I mean, if it is 0, then this is not occurring at plus minus omega naught. It's only at omega naught. That's it. If you consider a cosine function, but then there will be an impulse on the other side as well, okay, which is not the case over here. So for this single-sided or such functions, let me put this in a more broad sense. Such functions which do not obey Dirichlet's condition, then their Fourier transforms will exist. They may exist if you allow the existence of delta functions in their transforms. So, for example, you will unit step function is another function. I mean, in terms of xt, if you replace xt by ut, it also has a Fourier transform in terms of delta t, in terms of delta omega. Okay, and ut is also not absolutely integrable, right? I mean, it starts with 0 to infinity. This integral doesn't converges, right? So you can also go ahead and, I mean, to make the things easier, to make the analysis easier, you can take the reverse transform to show that, okay, if the transform of ut is given in terms of delta function, you can take the inverse transform to show that xt is indeed ut, or xt is indeed ej omega t. So since xt and the transform has a one-to-one mapping, so it doesn't matter which way you go, but this representation is unique. Okay, if you can go in the forward direction, if it obeys Dirichlet's condition, it's easier. If it does not, then you can always go back, take the inverse Fourier transform, show that this is indeed the case. So the whole story was that for ej omega naught t, this is the Fourier transform, okay, and ej omega t doesn't obey Dirichlet's condition, so the delta function exists in its Fourier transforms, and since it's not a real valued signal or a so its transform is also not symmetric. Basically, it's one-sided transform. Okay, so since there is a one-to-one mapping, xj omega is indeed the Fourier transform of xt, which is ej omega naught t. Now let's get back to the same problem. So more generally, what we're discussing was that more generally, if xj omega is of the form of linear combination of impulses equally spaced in the frequency, so if we have a linear combination of impulses like this in transform domain, then we can always to find its xt, well, we can always use this inverse Fourier transform relationship. If you do that, well, let's do that over here. Again, xt will be 1 over 2 pi. Then you bring this expression over here, and there will be a cancellation of 2 pi. Anyways, let's write the integration limit first, minus infinity to plus infinity, and then inside of xj omega, I can go ahead and write the summation itself. This is 2 pi, summation is over k. Both integration and summation operations are linear, but they're independent. So we can interchange their operations order as well. Okay, which is done first is not important. So this is omega minus k omega naught t, minus k omega naught. And then what else are we missing? Then there is an exponential that multiplies the whole expression. So dot e j omega t d omega. Okay, so what you can do is you can interchange the order of integration and summation. This 2 pi, it cancels, and you can bring the summation first. Okay, summation is over k, it's independent of integration. Okay, the integration variable is omega, so it has relevance. So you can bring the Fourier coefficient with it. Okay, AK, and then you recall that this delta function is multiplying by ej omega t with integration variable omega. So the result of this multiplication will yield ej k omega naught t over here. Okay, which is indeed completes the Fourier series representation of the signal. This is the Fourier series representation of a periodic signal, and what we are left with the integration is simply the delta function. Okay, there will be a delta function in there. So you recall that the area under this delta function is 1, right? That's the definition of delta function. So indeed, if you consider the square pulses, which are the impulse function, which is occurring at plus minus k omega naught, okay, in a periodic manner in frequency domain. So you have a pulse train in frequency domain, right? So at k equals 0, this is delta omega. Then the other pulse comes at omega naught. Then you have at plus minus omega naught. Okay, so this scale is omega 0, omega naught, minus omega naught, and then this trend continues. Okay, so then second impulse is 2 omega naught. So then this continues. Okay, this is 2 omega naught. So minus 2 omega naught. So we have this impulse train, right? But what is the area? The area of these pulses or the strengths are 2 pi times the Fourier coefficients, AK. Okay, so it's not a naught over here, but it has to multiply by 2 pi. Okay, that's the strength. So all the impulses are not being multiplied by the Fourier series coefficients only, but they have to be scaled by 2 pi as well. So that's an important relationship that occurs in the Fourier transform relationship of periodic signal. Fourier transform in representation of Fourier transforms of periodic signals, the Fourier series coefficients get multiplied with 2 pi. Okay, that's the first thing to notice. The second thing to notice is that, okay, if you consider this to be well, this is a periodic impulse train in frequency domain, but for if you consider this for this, we are talking of periodic signals. So let's forget about aperiodic for now. But just to remind you, if capital T increases, then omega naught decreases, right? I mean, if this omega naught is going to decrease for increasing T, right? That means if you have a periodic function in time domain, and if you're going to increase its period, then that periodic function is going to, I mean, the repeating periodic function is going to be separated apart, right? But the reverse happens in the transform domain. These impulses, they become much bunched together, okay? And so if you have for example, if you increase the period in time domain, then reverse happens in the transform domain, okay? The harmonics, they get closer and closer together, okay? That was the idea of aperiodic signals, okay? So these are two things. So if you increase the time period, then these impulses, they become bunched together, they become closer together. And the second one was that this area of these impulses, the strength of these impulses, is not the Fourier coefficients only, but it also multiplied by 2 pi. Okay, so any periodic signal that is represented by Fourier series has a one-to-one correspondence, one-to-one mapping with the Fourier transform, which is also periodic in frequency domain, consists of impulses, and these impulses are occurring at the harmonics of fundamental frequencies. We're having strengths of 2 pi ak, okay, ak being the Fourier coefficient. Hence, the Fourier transform of a periodic signal with Fourier series coefficients ak can be interpreted as a train of impulses occurring at harmonically related frequencies, which with the area impulse at kth harmonic frequency k omega naught is 2 pi times the kth Fourier series coefficients. Now to understand this one-to-one mapping between the Fourier series representation of periodic signal and its transform in terms of harmonically related impulses in frequency domain, let's take some examples. And one important thing is that you must remember that the samples of the transform are not the Fourier coefficients exactly. It has to be multiplied by 2 pi when we are considering the Fourier transform representation of periodic signals. We just don't have this Fourier series coefficients as the weights of the impulses. Those weights have to be multiplied by 2 pi. Okay, so for example, now this is example 4.6 in from your course text. This elaborates this point that it's not the Fourier coefficients that you have; they have to multiply by 2 pi. Okay, so let's consider again the square wave illustrated in figure 4.1. Well, we have seen that square wave before. If you recall, the square wave was of rectangular pulses. So basically, these pulses were repeating, and if this is 0, then this is t, then minus t, and these things, this spectrum continues. Okay. So for this signal xt, the Fourier series coefficients that we evaluated were of this form. Okay. But if you are going to use the Fourier coefficients for to evaluate the Fourier transform, then the Fourier transform, AK has to be multiplied by 2 pi. That's the first thing. And then it comes delta omega minus k omega naught being 2 pi by t. So in transform, you have this delta omega minus k omega naught, and you have to multiply AK by 2 pi. So multiplying 2 pi, 2 is there, and then pi cancels out over here. So that's the Fourier transform of a periodic impulse train, right? So it's just the Fourier coefficients that are scaled with 2 pi, and in the frequency domain, you see the Fourier transform of a symmetric periodic square wave. Because the periodic wave is, the periodic square wave is real and symmetric. The Fourier transform is also real and symmetric. It's just the Fourier coefficient that get multiplied by 2 pi. For example, this happens at this is at k equal to 0. Okay, and then you have the first harmonic at k equal to plus minus 1, plus minus 2. Okay, so it's just the Fourier coefficient being multiplied by 2 pi. Then that's it. This is sketch for figure 4.12. Okay, this is 4.12. Show the Fourier transform, and this is for t equal to 41. Okay, so in comparison with figure 3.7a, the only difference are the proportionality factor of 2 pi and the use of impulses rather than a bar graph. So we have the impulses basically; those are sampling the sinc function, and this sinc function is the envelope of the Fourier transform. Okay, which is continuous function of omega. Okay, now let's take another example which gives an intuitive feeling of this, the intuition behind the 2 pi multiplication factor. Well, the Fourier series coefficient, if you expand this in terms of Euler's, this is 1 over 2j, and you have e, j, omega naught t, minus e of minus j omega naught t. So you can see that you don't have any DC quantity because the average of the sine wave is 0, so there is no DC. But the Fourier coefficients of a plus minus 1 are 1 over 2j and minus 1 over 2j. There is a minus sign over here. So AK is 0 for k not equal to 1 or minus 1. Okay, so basically you just have a equal to a1 and a minus 1. And other than that, AKs are 0 if k is not equal to 1 or minus 1. So similarly for cosine function as well, you can expand this in Euler's, and this is 1 over 2, say 2. So instead of 1 over 2j, this is 1 over 2, and the same story repeats. So how can you represent this in terms of Fourier series? This is the Fourier. How can you represent this by Fourier transforms? Okay, this is the representation in terms of Fourier series. Okay. We can find the Fourier coefficients directly. Just comparing this with the Fourier series representation, we know what AKs are. This is k omega naught t. Now, what we are interested is to have a look how does the Fourier transform represent sines and cosines. So you see, we recall that it has a one-to-one mapping with Fourier transform xj omega, which is nothing but a constitution of periodic impulses having the weights as 2 pi times AKs, right? 2 pi times the Fourier coefficients, right? And this has to multiply by delta omega minus omega naught, right? So what do you expect? Look at this. This is k, so this is k omega naught. So, well, since there are only two Fourier coefficients, it turns out that for sine omega t, x of j omega, okay, let me put the x j omega over here as well. So x j omega, since k for this summation, k is equal to plus minus 1 only, otherwise it is 0. So that means this will be equal to, I have to multiply this with 2 pi, so this becomes pi by j, okay, pi by j. So the first impulse occurs at, this is for k equal to 1, omega minus omega naught, and then I have the second Fourier coefficient minus 1. So for that it is minus pi by j, okay, minus pi over j delta of omega plus omega naught. That's it. This is the Fourier transform of a sine function. Okay. Similarly, if you have to do this for cosine, then my x of j omega will be 2 pi times the Fourier coefficient. So just multiply this with 2 pi. The Fourier coefficients are 1 over 2. So that means it will be pi of, then I can write this. This is the same Fourier coefficient for both a1 and a minus 1. So this is delta omega minus omega naught plus delta of omega plus omega naught. That's it. Okay, so you see, well, there's another way of looking at this in a simplified manner. Since cosine and sine consist of two exponentials, right? And we know that e j omega naught t, what we derived earlier, has a Fourier transform which exists in terms of a shifted impulse. Okay, the Fourier transform is 2 pi delta of omega minus omega naught, right? I mean, this is what this is how we started with the discussion of Fourier transform representation of periodic signal. This is the Fourier transform of xt, right? E j omega naught t. So cosine and sine consist of two exponentials, right? So of course there will be two delta functions. It's just the Fourier coefficients that are going to be multiplied by 2 pi. So for example, 1 over 2j and 1 over 2 is going to multiply by 2 pi. So that's it. I mean, you will have the impulses with having weights of pi over j and minus pi over j for sine function, and then pi for a cosine function. Okay. So if you understand this representation, that okay, xt is periodic and can be represented in Fourier series, then it will have a Fourier transform in which the Fourier coefficients will be scaled by 2 pi. Other than that, you have these impulses, right, in transform or in the frequency domain, which is repeating at the multiple of harmonics of the fundamental frequency. So this is the representation of Fourier transform representation of periodic signals for cosine and sine. Okay, all right. Now let's take another example, 4.8. The signal that we'll find extremely useful in our analysis in sampling systems is the impulse train. Okay, so I've talked about this a while before. So for sampling process, let's consider a switching process, okay, which happens at a multiple of switching time t. Okay, so you can think of this as an impulse which is occurring at, for example, minus t at 0. Then so I mean, for k plus minus 1, this is the situation for k equal to 2, 3, and so on and so forth. K is an integer multiple of this switching instance of time. This is a periodic impulse train, so this can be represented. I mean, this is the representation of a periodic impulse train in the time. So this is periodic with period t, so that means it can be expressed in terms of Fourier series. So this is shown in figure 4.14a, and this is figure 4.14a. So you can see this xt consists of periodic impulses having the period t. So for example, this is minus t by 2 plus t by 2. This is in one period you have just a single impulse, and then it is repeating at interval of capital T. So the Fourier series coefficients of this signal were computed in example 3.8. And if you recall the Fourier series coefficient, how they're computed is 1 over t minus t by 2 to plus t by 2 over one period. For one period, it's just delta t, right? I mean, look at the depiction. It's just delta t. Within one period, it's just delta t. And this greatly simplifies the Fourier analysis equation to find the Fourier coefficient. So we have delta t over here. And then this, since this exists at t equal to 0, so this becomes 1. and delta t dt is 1, so you're just left with 1 over t, and this is the situation for all k. So for all Fourier coefficients, well, all Fourier coefficients have the same value or the strength, that is 1 over t. So every Fourier coefficient of the periodic impulse train has the same value, that is 1 over t. Okay, so how to construct the Fourier transform representation? Well, that's simple. You know that xj omega will be consisting of periodic impulses in frequency domain. It's just the Fourier coefficient that gets multiplied by 1 over t. So 2 pi by t becomes 2 pi ak multiplied by delta of omega minus k omega naught. That's it. This is the Fourier transform. Very simple. You don't have to even, go ahead and take the forward transform of delta functions like that. You just know that it's a periodic function, and the periodic function can be expressed in terms of Fourier series. If the Fourier series exists, then it has the Fourier coefficients. Just multiply those Fourier coefficients with 2 pi, and that's it. You are done. So xj omega is 2 pi by t, and this is the expression. So note that this 2 pi by t is your omega naught, right? So it's k omega naught. Omega naught is 2 pi by t. So that's the Fourier transform of a periodic impulse train. Fourier transform of a periodic impulse train in the time domain with period t is periodic impulse train, again frequency domain with period 2 pi by t. This is sketched in figure 4.14b. So you can see over here, this is your, for example, this is sketched for k equal to 1 over here, and then from k equal to 2, this is 4 pi by t. Again, this is periodic, okay? And the Fourier coefficients are multiplied. Fourier coefficient 1 over t is multiplied by 2 pi by t. So this is a representation of, in figure A, you have the periodic impulse train in time domain. In part B, you have the Fourier transform of it. Okay, xj omega. It's just the Fourier series coefficients multiplication with 2 pi, and the rest is the repetition. Okay, the rest is the impulse train. So you also notice over here, if you increase t, if t is increased, and this implies, what does this imply? This implies omega naught decreases, right? Omega naught decreases. What is omega naught? Omega naught is 2 pi by t. So that means as the period is increasing, the impulses are shifting away in time domain. In frequency domain, they're getting closer and closer, right? So it's the other way around. So you see here again, we see that the illustration of the inverse relationship. Okay, we have seen the inverse relationship of the time and the frequency domains. So as the spacing between the impulses in the time domain, the period gets longer, the spacing between the impulses in the frequency domain, namely the fundamental frequency, gets smaller. So that's the idea. The idea is that first of all, your Fourier coefficients, they get multiplied by 2 pi. Okay, so it's 2 pi times the Fourier coefficients, and then rest is just the representation of Fourier transform in terms of periodic impulses in frequency domain. So that's the Fourier transform representation of periodic signals. So Fourier transforms are valid for even broader class of signals in a very broad sense. If the Fourier coefficients exist, then it doesn't matter if a signal is aperiodic or periodic. Fourier transform is applicable, and it's valid if the Fourier series coefficients are finite and the Fourier transform integral converges. Okay, and again, Dirichlet's conditions are for convergence, they are sufficient, but they are not necessary. Okay, so for such functions which are not absolutely integrable or which doesn't have a finite energy, doesn't mean that the Fourier transform doesn't exist. It will exist, and it will exist in terms of impulses. Okay? And you can show this in a reverse manner. So that's what we have done. So xj omega for the Fourier transform of a periodic signal is also periodic. In frequency domain, consists of impulses which are harmonically related. Okay, and their strengths are multiplied by 2 pi. So the Fourier series coefficients are just multiplied by 2 pi. That's it. If you have the Fourier coefficients that multiplied by 2 pi, put them in the summation, and you can see the Fourier transform representation of our periodic signal. Okay, that's all.